In the 1970s, architect Laurie Baker was building houses in southern India and doing something with concrete roofs that, at first glance, looked almost absurd. Before pouring the slab, workers placed ordinary clay elements between the reinforcement, tiles, hollow blocks, and sometimes even upside-down pots. In other words, part of the future concrete roof was deliberately replaced with cheap fired clay and empty air. And the strangest thing was that this did not weaken the basic idea of the roof itself. On the contrary, such a structure could require noticeably less concrete and steel, become lighter, and at the same time protect the rooms from heat more effectively. In materials on cost-effective construction, filler slabs are associated with approximate savings of up to 30% in concrete and up to 40% in steel in suitable projects. But this raises an obvious question. If the solution is so simple, cheap, and has been known for decades, why is it hardly seen in ordinary construction in the United States and Europe? The answer is more complicated than it seems. To understand why anyone would hide clay pots inside a roof in the first place, we first need to see the problem with an ordinary concrete slab. In a hot climate, a flat concrete roof stays under the sun all day. Concrete is massive and conducts heat well. It gradually heats up, stores energy, and then transfers it into the building. The most unpleasant part begins toward evening. The sun is already going down. The outside air is getting cooler, but the heated slab continues releasing the stored heat downward. It becomes a huge thermal battery directly above your head. These were exactly the kinds of problems Laurie Baker constantly dealt with. British by birth, he spent most of his life working in India and became known for looking for ways to build with local materials instead of relying on expensive universal solutions, reducing the use of cement, steel, and energy. One of the techniques he actively used was the filler slab, literally, a slab with filler. This technology is still among the recognized methods of economical and environmentally oriented construction in Kerala. But here is what matters. The point of this technology is not really the pots themselves. To understand this, imagine an ordinary reinforced concrete slab spanning a room. Under load, it tries to bend. The upper part mainly works in compression, while the lower part experiences tensile stresses. Concrete handles compression extremely well, but performs much worse in tension, which is why steel reinforcement is placed in the lower part. And this is where an interesting opportunity appears. In certain parts of the slab, some of the concrete mass in the tension zone contributes less to resisting bending than the concrete in the compression zone. Of course, concrete is still necessary around the reinforcement for bond, protection, and force transfer. But making the entire internal volume of the slab completely solid is not always necessary. And if part of the unnecessary dead weight is removed, the concrete can be kept exactly where it is really needed. This is where hollow clay elements come in. First, the formwork is installed and the reinforcement designed by the engineer is placed. Then a lightweight filler is placed between the ribs. For example, clay tiles, hollow blocks, or pots. After that, concrete is poured so that reinforced concrete ribs and the upper layer of the slab form around the filler. As a result, the roof remains a reinforced concrete structure, but inside it, there is no longer a continuous mass of heavy concrete. And even if the story ended only with weight reduction, the technology would already be interesting. But that is only half the story. Each hollow element creates an air cavity inside the roof, and still air conducts heat much worse than dense concrete. It is the same general principle used in double-glazed windows, insulated panels, or thermos flasks. Instead of a continuous path through a dense material, heat has to pass through layers with much lower thermal conductivity. So a filler slab solves two problems at once. It removes part of the unnecessary mass and at the same time makes the path by which solar heat travels through the roof into the room more difficult. And studies show that this is not just an attractive theory. Research on filler slabs considers such structures specifically as a way to reduce heat transfer through the roof, and studies in warm and humid climates show improved thermal comfort compared with conventional reinforced concrete solutions. The result depends on the specific design, so promising a universal -10 degrees would be incorrect. But the overall picture becomes very interesting. Less concrete, lower self-weight. In some projects, less reinforcement, less material that needs to be produced, transported, and lifted onto the building. And in a hot climate, also less heat entering through the roof. And now the technology starts to look almost too good. So why aren't modern houses built this way everywhere? This is where the story changes sharply. The first obstacle is labor. Where filler slabs historically developed, the filler elements could be made from cheap local materials, and a significant part of the work was done by hand. But in countries where skilled construction labor is expensive, a few extra hours of manual work can easily consume the savings on concrete. The filler elements have to be prepared. They have to be positioned precisely relative to the reinforcement. They have to be secured. They must not be allowed to shift during pouring. And the concrete has to be carefully distributed around the ribs being formed. For a large contractor, a standard solid slab is often faster and more predictable, even if it requires more material. But labor cost is not the main barrier either. The second problem is building codes and engineering calculations. A roof is not a decorative panel. It is a load-bearing structure that remains above people for decades. An engineer has to confirm its strength, deflection, reinforcement, steel protection, durability, and other parameters. And the idea of voids inside a concrete slab has not disappeared from modern engineering at all today. Industrial voided slabs exist in which special elements also displace part of the heavy concrete. So the principle is still alive, but a random set of clay pots does not automatically become a certified building system. And then another problem appears, one that is very easy to overlook in a beautiful photograph of a house somewhere in the tropics. Climate. Clay, concrete, steel, and water have to work together not for 1 year or 5 years, but for decades. In a warm climate, a properly executed filler slab can be durable. Baker himself described the reinforced concrete filler slab roofs he used as cool, waterproof, and permanent structures. But in humid regions, and especially where freeze-thaw cycles are possible, the choice of the clay itself, its water absorption, frost resistance, waterproofing, and protection of the reinforcement become much more important. In other words, you cannot simply take an ordinary flower pot, embed it in concrete, and assume the problem is solved. And this is where one of the details capable of destroying all the advantages of this idea appears: the protective concrete cover around the reinforcement. If the steel is too close to a damp filler element or to the outer surface, moisture and aggressive substances can reach the reinforcement more easily. Corrosion begins. Rusting steel increases in volume, creates pressure inside the concrete, and over time can cause cracking and delamination. In other words, a mistake that is practically impossible to see after construction is complete may reveal itself only years later. And this is not the only detail. Porous clay elements are often wetted before concreting so that they do not draw water out of the fresh concrete mix. The filler must be held in place, and the concrete around it must be compacted in such a way that the fragile elements are not damaged, while at the same time no voids are left in the load-bearing ribs. And after all of this, it becomes clear why the technology never became a universal DIY home hack. It really can be cheaper, lighter, more material efficient, and significantly more interesting for a hot climate. But this is not a technology that can be added to an existing roof over a weekend. It has to be part of the design before the slab is poured. The spans, loads, reinforcement, concrete thickness, rib dimensions, and location of the voids must be calculated by a specialist. And perhaps this is the most interesting part of the whole story. Laurie Baker did not discover some magical material of the future. He did almost the opposite. He looked at an ordinary concrete slab and asked an unusual question. Which part of the material could simply not be used at all? The answer turned out to be cheap clay and empty air. For one climate and one building culture, this idea can be surprisingly sensible. For another, it can lose out because of labor costs, building codes, or durability requirements. But the principle itself has not disappeared. Modern engineers continue to create voided concrete structures according to the same fundamental logic. If a heavy material does not contribute enough to the structure to justify its weight, perhaps it simply should not be there.